Hello and welcome back, Math 30-2. Today, we're going to be looking at logarithmic scales and their applications. So our first set of examples, we're looking at the Richter scale and earthquakes. Okay, so that was a big one. Now, earthquakes are named after American seismologist Charles Richter. There we go, get everything back set up. Now, basically, what he did was he looked at it. 1 point on the Richter scale is equivalent to 14 kilograms of dynamite going off, all right? And every time we go up by 1 point, right, we're going up by 10 times the intensity or the strength of our earthquake, okay, or the explosion, the shaking is 10 times the strength every time we go up by 1 to the power of 10, okay, 10 to the power of something. So here's a little example for me to explain what I mean. An earthquake of the magnitude of 8 is how many times as intense of 1 by the magnitude of 7. So if I look at this, this increases by a magnitude of 1, which is 10 to the power of 1 times as powerful. Our next one here is an earthquake of the magnitude of 7 is how many times as intense as an earthquake of the magnitude of 3. Well, that's going to be, according to the Richter scale, 10 to the power of 4, which is 1,000 times more powerful. Our next, 10,000 times, not 1,000, 10,000 times more powerful. Next one says an earthquake of the magnitude of 4 is how many times as intense as an earthquake of the magnitude of 6. Here I'm going to go 4 subtract 6, which is 10 to the negative 2 times as powerful. And now here it says an earthquake of magnitude of 4.8 is how many times as 6.8? Well, we go 4.8 subtract 6.8 is a difference of negative 2. So that's, again, 10 to the negative 2, which is 1 over 100 times, or 100th as powerful. Okay, next one here. We have a 1960 earthquake in Chile. Okay, so that was, on the Richter scale, 9.5. And we want to know how many more times intense of this as the earthquake in Italy, and how many more times intense as the earthquake in Colombia. So we first look at 1976, earthquake in Italy, 1976, that's Guatemala, Italy, 6.5. So we went from 9.5 to 6.5, so we subtract those, it is going to be 10 to the power of 3 times as intense, right? 9.5 subtract 6.5, which is a total of 1,000 times more intense. Now, how much more times intense is it than the 1983 Columbia? I go back up here. 1983 Columbia is right there. So 9.5 subtract 5.5 is 4. So it's 10 to the power of 4. So it's 10,000 times as powerful. Okay? Now we're going to look at the 1966 earthquake in Turkey was how many times as the 1933 in Japan? Well, let's find Turkey. 1966, 6.9. Japan is up here. Which Japan? 1933 Japan is right there. 8.9. From 6.9 to 8.9. We subtract them. I'm going to get 10 to the negative 2, which is 100th as powerful as the one in Japan. Comparing earthquake intensities. This part here, you guys should maybe first go over a bit. I suggest you try and discover that and try that on yourself. I'm going to continue over with class example number 2. It says, how many times more intense was the 1960 earthquake with a magnitude of 9.5 than the 2005 earthquake in Chile with a magnitude of 7.8? So I'm going to use this formula right here. We want to know how many more times is intense. So intensity of this one divided by the intensity of this one is equal to 10 to the, well, we want 9.5. Because this one, how many more times is intense is this one than the 7.8, right? That over that. Which will end up giving me 10 to the power of 1.7, which is equivalent to, if we plug it into our calculator, 50 times as strong. Okay? Let's take a look at the next one. It says, a major earthquake of a magnitude of 7.5 is 375 times as intense as a minor earthquake. Find the magnitude to the nearest tenth of the minor earthquake. So we have 375 is equal to 10 to the power of 7.5, subtract whatever my minor one is. Now, here's my problem. I don't know an exponent. I can't. 10 to the power of this is that. So I'm going to put this in log form. So I know log 10 375 is equal to 7.5 subtract m1. Okay? Now, what I could do is I'm going to solve for my minor earthquake, my magnitude of the minor earthquake, which is equal to, we have 7.5 subtract log 10, and we have 375. So I put this into my calculator, and I'm going to end up getting a total of 4.9 is going to be my magnitude, approximately. Okay? All right. Now we're going to look at loudness of sound. Loudness of sound is measured in bells, named after the great Alexander Graham Bell. Now, decibels is the other unit we use, which is 10 decibels equals 1 bell. All right? Think of the word deci in there. Now, the bell is very close to the Richter scale. All right? When we increase in bells, we're increasing of a magnitude of 10 to the power of something. So an example would be the rustling of leaves outside, so something like this, a little bit of rustling, if you could hear that, is equal to 1 bell, which is 10 times the threshold of hearing. So therefore we could hear it. A little whisper like this, is the same as 3 bells, which is 1,000 times the threshold of hearing. And then it is only, if we hear this rustling of paper, it is only 100 times the intensity of the rustling of paper. Now, let's go and take a look at this here and complete our examples to help us understand it a bit more. A power saw is 120 decibels. All right? Is how many times as loud as a telephone dial of 80 decibels? Well, this is the same as 12 bells, and this is 8 bells. The difference is 4 bells. So that is 10 to the power of 4. The power saw is 1,000 or 10,000 times more powerful sound-wise than the phone, which makes sense. Power saw is a lot louder. Here we go. Let's look at the next one. A jet engine of 20 meters above you is 145. So that's 14.5 bells. Now we want the sound, the threshold of pain is 12.5 bells. Well, yeah, I'd say a jet 20 meters above you is going to be above the threshold of pain because it's pretty loud. Now, we subtract these, it is going to be 10 to the power of 2, which is 100 times. Okay? Now, a whisper is 30 decibels, so that's 3 bells. And it's how many times as loud as a loud conversation of 6 decibels? Well, I subtract these, I get 10 to the negative 3. So it's 1,000th as loud as a conversation, as a loud conversation. Okay, so now let's compare sounds using some of our formulas here. All right? We have given, our formula here, show that the decibel level of pain, 1,000 or 125 decibel, is the same as the sound intensity level of 10 to the power of 12.25 naught, okay? Or intensity times the original intensity. So let's take a look at this. I have, here we go, we're going to have 125 is equal, plug this into our formula, 10 log I over I naught. All right, now we want to solve for this I. How do I do that? Well, I'm going to have to try and put this into exponential form, but first I'm going to put the log by itself by dividing everything by 10. So I get 12.5 is equal to log I over I naught. Now, this is my sound barrier, okay? So now we're looking at this. Can't solve this, so I'm going to put it into exponential form. So I have 10 to the power of 12.5 is equal to I over I naught. Then multiply both sides by I naught, so I get I naught multiplied by 10 to the power of 12.5 is equal to my intensity. Okay? Let's take a look at this one. How many times more intense is the sound of a piano playing than a whisper? Okay? So for this one, we're going to use this equation here. right? Or I'm going to use this one here and convert them into bells. So this is 2.2 and 6.7. All right, otherwise I have to divide that by 10, but we could do that beforehand. So my intensity, which one is it? Piano over I whisper is equal to, we're going to have 10 to the power of 6.7 subtract 2.2, which is equal to 10 to the power of 4.5, which gives me approximately 31,622 times. Okay, so I put this into bells, divide both of those by 10. Now our next one here says, 2 telephones in a home ring at the same time with a loudness of 80 decibels. Does this mean that their total loudness is 160 decibels? Explain why or why not using sound intensities and the properties of logarithms. Okay, so I'm going to start off by saying my x is equal to my total sound. Okay, sound loudness. Okay, well, x bells. We'll put it in bells. Make sure it's in bells. Now, I'm going to say then my intensity is equal to 10 to the x multiplied by my intensity threshold. Okay? Well, I look at this now. We have 10 to the x multiplied by intensity threshold is equal to, well, we're adding 2 of these together. So that's 10 to the, well, that would be 8 bells. Okay, I multiplied by intensity threshold plus 10 to the 8. Okay, so we have all of those. Now I simplify this. This is going to end up giving me 10 to the x is equal to 2 multiplied by 10 to the 8, because there's 2 of them, we're adding them together. All right, there we go. Now I can simplify this. I'm going to divide both sides by I naught, so these will cancel off, and I'm left with this here. So I'm left with 10 to the power of x is equal to 2, 10 to the 8. Now my problem is, I cannot get this to the same base as that, can I? No matter where I move that. So I'm going to have to log both sides. So I'm going to log to get my exponents down. Log 10, and that exponent goes there, is equal to log 2 plus 8 log 10. So that put down my exponents. I just kind of combined some steps into one there. Now I look at this, 10 to the power of what is equal to 10? 1. So I'm just going to get x here. This is still log 2. Now 10 to the power of 1 is equal to 10? 1. Multiplied by 8 is 8. Plus 8. So we end up getting, I'm going to write this down here, we end up getting, if we add these together, 8.3. Okay? So my x is equal to 8.3. So it's going to be the same as 8.3 or 83 decibels. Okay? Which isn't even close to 160. Okay? Because we're doubling the loudness. We're not. This would be like a lot. That's like 80 times 10 to the, okay? It's like 8 times 10 to the whatever. That's more than doubling. We'd have to multiply by that. Okay? Now we're going to look at pH scale. So the pH was invented by a Dutch person named Søren Sørensen, okay? And what pH stands for is also known as the power of hydrogen. Now I look at power. What does power mean? Reminds me of exponents. So maybe we use exponent laws here, which are related to logarithms. Okay, so let's take a look at this. Here's my scale. 7 is neutral, neither alkyne, which is base, or acidic. Now the higher the concentration level, right, the more acidic it is. The higher the concentration of hydrogen, the more acidic. The lower the concentration level, the less acidic. But these are very small levels of concentration. They're all to the negative if you look at. So I'm going to go over some examples here to help us discover this, okay? So, tomato juice is how many times as acidic as pure water? Okay, so we're going to look at tomato juice is 4, pure water is 7. So that is -4 subtract -7. I always go with the negatives of these because I always find out the acidity and then go back. So this is 10 to the, and this will give us 3, which is 1,000 times more acidic. Eggs are how many times more alkaline than pure water? So this wants base. So we want eggs and pure water. So that's 10 to the negative 8 subtract negative 7, which gives me 10 to the negative 1. So it's 1/10 as acidic, so that means it's going to be 10 times more alkaline, because alkaline is looking at the base. Now, the next one is milk of magnesia, which is 10.5, is how many times as blood? Blood. There we go. Where's blood? 7.5. So that's going to be 10 to the power of 3. 10.5 minus 7.5. Or 10.5, negative 10.5, subtract 7.5 is 10, or is 3, is to the negative 3. It gives me 10 to the negative 3, right? So if it's negative, I put that positive, that's going to be alkaline. All right? If I kept it negative, I would say acidic. Okay? Now, let's take a look at this one. Something is hundreds of times as acidic as rain. So here's normal rain, and I want to be acidic, so we have to be positive. So is more acidic than rain? So let's take a look at this. 3 subtract negative 5 gives me 10 to the 2. This one here is more acidic. Negative 3 subtract negative 5 is 10 to the 2. So we're going to have vinegar. Now the last one is eggs are how many more times as alkaline as soda water? So we have eggs and soda water. Washing soda. 12 and 4. So that's alkaline. We have to leave it. We subtract this from this. We're going to get negative 4. So it is 10 to the negative 4. So it's 1/10,000th as alkaline. Okay? All right, so now let's go to some questions here to work at under pH. It says pure water, swimming pool water, and seawater all have pH levels of 7, 7.5, and 8.4 respectively. How many times as alkaline is seawater than pure water? So let's take a look. We want to know seawater compared to pure water. So that's going to be 10 to the negative 8.4 subtract negative 7. Okay? How many times is alkaline is seawater than negative water? Which gives me 10 to the negative 1.4. And as I said, this is going to be more basic because I always do mine in acidity, so this is going to be more basic. So it's 1 over whatever for acidic, so basic is going to be the other way, 10 to the 1.4, which is equivalent to approximately 25 times. Okay? How many times as alkaline as swimming pool water is seawater? So here we're going to go seawater to swimming pool. 10 to the negative 8.4 subtract negative 7.5. So it is 10 to the negative 0.9 more acidic. So basic, it is 10 to the 9.9, which gives me approximately 8 times. All right? So let's take a look at question example number 10. It says a patient gave a urine sample which found to have a pH of 5.7. What was the hydrogen ion concentration? So now we're going to use this formula here. So we know pH is equal to, so we have 5.7 is equal to negative log and my hydrogen concentration. Okay, so, and we're trying to find out what was the hydrogen concentration. Now I look at this, I want to get that log by itself, so I get negative 5.7 is equal to log. Now I can't solve for this, so I'm going to put it in exponential form. So this is, there's an imaginary 10. 10 to the power of negative 5.7 is equal to H, which will end up giving me a total of 2.0 times 10 to the negative 6 moles per liter. All right? Let's take a look at example number 11. This is determine the pH of a solution to the nearest tenth if the hydrogen concentration is 3.4 times 10 to the negative 4. So now we know my hydrogen concentration. Okay? So we have pH is equal to negative log, and we have 3.4 10 to the negative 4. Now I'm going to just plug this into my calculator because it's already right there, and I'm going to end up getting my pH is equal to 3.5. And that is it. Okay? Hopefully you understood that. If you have any questions, feel free to ask tomorrow as we work on the assignment together as a class. See you tomorrow.